Hi everyone. I thought I would do some quick notes on polar coordinates in case this is still a little foreign to some people. I think it might be worth taking a little bit of a step back and doing a simpler example of rotating Cartesian axes before we get to polar coordinates. So there'll be rotation matrices, polar coordinates. So you can use the video description if you want to skip around or listen to this briefly. So again, quick reminder on coordinates, and I will go fast. Usually I don't like to have it already written out because writing it out myself slows me down. So I will probably talk fast, but again, this is hopefully a review, and you can watch it again if you need to hear it again. So Cartesian axes. We have some fixed x and some fixed y. But the idea with Cartesian is that they are fixed. They are anchored down and do not move with time. So we have some position, which we can define a position vector from our origin. I'm allowed to put my coordinate axes wherever I want. I can put my axes oriented in some way, like I've done here, and I have my origin at some location. That then allows me to define a position vector that goes out to that point, and I can decompose that position into an x component and a y component. The amount or the distance that the object or the particle or whatever it is along each particular axis. And of course I can write position as that component times the axis of that component. So we have x in the x-hat direction, y in the y-hat direction. We write it like this. This is just, a compact way of doing it. But when we write it like this, we have to remember what the actual unit vectors are. So this is the same as this. So the first component is saying something about what's going on in the x-hat. Second component is saying what's going on in the y-hat. So again, if we want to be really detailed about what we're doing, suppose the question is we want to determine the trajectory when the force vector is given by this in Cartesian coordinates, with our initial position is this, our initial velocity is this. So again, since Cartesian coordinates are anchored down, they're absolutely fixed. We probably never said this explicitly in intro physics or in any math course. But what that's saying is that these unit vectors are not functions of time. So that when I take derivatives, these unit vectors do not have some sort of non-zero derivative. So if we start very generally, I can define my position as x comma y in this 2D Cartesian system. Then the velocity, by definition, is the derivative of that vector, which is then the time derivative of this entire thing when I write it out with the unit vectors. By linearity, the derivative distributes, and then by the product rule, this derivative is then applied to x times x hat, and then x times the derivative of x hat. But since we just said that the time derivatives of the unit vectors are 0, the product rule just becomes simply x dot x hat plus y dot y hat, where again I'm using the dot notation to specify a time derivative. The number of dots is the number of the derivatives. I can do that again. Acceleration by definition is a derivative of velocity, so then that becomes again, by same sort of thing, x double dot in the x hat direction plus y double dot in the y hat direction. So the interpretation then is that, and usually these are questions that you ask, like you could ask the general question, how does x change? How does your position along the x direction change? Well, that is just x dot. How does y change? Y dot. These are how these things change with time. So if I want to know how this coordinate changes with time, I have to go find or calculate x dot. Here, in Cartesian coordinates, we just have to look towards the velocity vector, and if this is the x position, then we just look at the same component in velocity, and that gives me x dot. Here this is y, and I look in the same component, and that gives me y dot. this tells me how this is changing. And that seems pretty straightforward. Similarly with acceleration and velocity. How is x dot changing? Well, that is x double dot. How is y dot changing? Well, that is y double dot. Again, in Cartesian coordinates, you simply just have to look at the same coordinate for the vector, and that tells you how it is changing. Acceleration says how velocity is changing. Velocity says how position is changing. And once we've started here very generally and define a general position and to get a general velocity and then a general acceleration. So in Cartesian coordinates, if you want to do f equals ma in this coordinate system, this is what you plug in for the acceleration. So going back to the original problem, if I know that f is this vector, I then set that equal, and usually the force is what you are trying to calculate, or what you kind of use all your physics skills to calculate. Including all the forces, look for anything that's touching your system. There's a contact force that results, and then include any long-range forces. Once you have that net force vector in this particular coordinate system, you then set that equal to m times the acceleration vector, which we derived up here, and then that just becomes this. That then gives you two differential equations that you can then solve using your initial conditions to ultimately get the trajectories for x as a function of time and y as a function of time. And you can look at that if you need a reminder. In this case, these are separable differential equations. All right. Hopefully none of that was surprising. Now, of course, we are allowed to put down our coordinate systems in any way we want. So Alex, for example, could put down his coordinate system that looks like this, and so that he could define a position vector based on where he put his origin and then he could decompose this position into an x and a y component based on how he laid down his axes. Casey, however, she could decide that, well, I want to have my axes pointing x in this direction and then y in this direction, and I'll call it y, y prime and x prime. So in this case, she could also define a position vector that goes out from her origin, but she is of course going to get different components when she decomposes it into a component along her x prime direction and her y prime direction. And so Alex could then define a general position like we did before as x comma y, take the time derivative of that then gives you a velocity as x dot y dot, similar for acceleration. Similarly, Casey could define a general position as x prime y prime. Again, remembering that this means in using the axes in her coordinate system, so using this axis and this axis, not what Alex has. So setting this equal to this, for example, would be silly because that makes no sense. And then she could take the derivative, and that then gives me a general velocity, for example. And if they compared notes, they would be able to confirm that it seems like they have the same coordinate system, but they've just rotated it. So Alex has his there, and if I take those and I rotate them counterclockwise by some angle theta, looks like you then get Casey's. So it looks like they're trying to describe the position of this coordinate here using two different axes, which is perfectly fine. They will get different numbers for their coordinates because their axes are different. But of course, it'd be nice if they want to compare notes, if they knew how to translate one coordinate system to the other. How can Alex turn his numbers into something that's on Casey's axes and vice versa? So how does the position in Alex connect to the position in Casey, and similarly for the derivatives? Now this is easier than polar coordinates because we're using two different sets of Cartesian axes, and both of them are anchored down. I don't have to worry about time derivatives for either of their unit vectors. So in this case, all you have to do is find out how the unit vectors transform and then you're done. Actually, that's true in general, but in this case, there is no time dependence. So let's try to translate Casey's into Alex. So I have Alex's coordinate system laid down. I'm going to start with the x prime vector. So as a good physicist, I look for triangles, and it seems like I have a nice triangle right here. And I can decompose it into an x component and a y component. And it seems that for this vector, which has length 1, that this vector is nothing more than cosine in the x direction and sine in the y direction. And that, of course, is just writing this vector as this plus this. That then has written her vector in terms of a combination of his vectors. Then similarly for y prime, you got this going on right here. You could also think of it as it being rotated an angle theta from the y hat direction. Or you could think of it as having some big angle here, if measuring from the x-axis. And so I redraw it over here. And so again, looking for triangles, I notice that there's a triangle right here, and I like to use angles that are less than 90 degrees when I'm dealing with these sorts of right triangles. So I know that this angle is theta, and so then that gives me, by SOHCAHTOA, I can easily get this length and this length. And and using SOHCAHTOA, I will of course get positive numbers if I use whatever this angle is, which is less than 90 degrees. Now then I have to be careful because I have to make sure that the signs match the directionality set by Alex's coordinates. So in this case, the y component here just becomes that, and that is pointing in the positive y direction. So in this case, here, that is this right here. And it's cosine because the swoosh touches this part, and the swoosh touches the cosine part. But then I have this component here, which by SOHCAHTOA, this triangle right here, would be sine. But since that it ultimately then is pointing in this direction, that is in the negative x hat direction, so then I write cosine of y hat plus sine times negative x hat. So then ultimately I get this as my decomposition of y prime into some component along the x direction, but since it's pointing this way, it's negative, and then some component in the y direction. So ultimately, it looks like I have this transformation. In order to go from, or in order to take this unit vector and write it in Alex's coordinate system, and then this unit vector and write it in Alex's coordinate system, this is called a linear transformation. We can also write this as the vector x prime y prime equal to this matrix, which has 4 components. There's no commas or anything. It's not dividing. Don't think of these as ratios, but these are 4 distinct components, and that's being multiplied. Should have been a little down here. That's being multiplied by this vector x hat y hat. So this is the matrix formulation for, and this is saying the exact same thing as this. The way we usually write it, or the way I like to write it, is we're saying that this vector r, well, I guess that's the generalization. This is telling you how the unit vectors transform. And of course, any vector is just, for example, 3 x hat prime plus 2 y hat prime, some general vector in Casey's coordinate system. That then, if I know how the unit vectors transform, then multiplying by 3 and 2 is pretty easy. And so in general, some general vector, give me any vector in Casey's coordinate system. And that is the same thing as having this matrix, this thing here, being multiplied by the position of that coordinate in Alex's system. So again, that we are found a relationship between Alex and Casey. In this case, the way it's written, give me the coordinate in Alex's system, I will multiply it by this matrix, and it will pop out ultimately the coordinate in Casey's system. And so again, this is a matrix, particularly as a 2 by 2 matrix, where the first number is the number of rows, row, row, and then the second number is the number of columns, column, column. And so this is a 2 by 2 matrix, or if you're feeling fancy or want to impress someone, you can call it a tensor. So what this is, and particularly this is what's called a rotation matrix. And I write matrices like this. I'm kind of mixing American and European notation. I kind of got hooked on the European notation and never went back. So if you ever see me kind of write kind of R and I write like a line under it, that is the same thing as just the vector. And then matrices are kind of a generalization, a multi-dimensional vector. So that is why we have the double line. Specify that it is a multi-dimensional vector or tensor compared to just a vector. Anyway. So, in this case, this matrix is a rotation matrix, and that what it is doing is that it is a rotation matrix that will turn Alex's coordinate system into Casey's coordinate system. I.e., if we go back up to the images here, what that does, it seems like you could imagine taking Alex's system and rotating it counterclockwise by some angle theta, and then this would become this, and then this would become that. So we could say that this is a rotation matrix that rotates the axes counterclockwise. And I highlight this because there are other rotation matrices that exist, and they accomplish different things, and online resources are often pretty sloppy about specifying what exactly the rotation matrix is doing. So here I'm being very explicit in saying that this here is a matrix that rotates the coordinate system counterclockwise by theta, i.e. turning the black into the salmon. And particularly that's accomplished by these formulas, which again is equivalently written like this, and this is kind of generally what we're doing here. So then the question is, how does this end up being the same thing as this? If you don't know how to multiply matrices, this might seem, you might see some connections, but it might be a little unclear kind of how you go about multiplying matrices and vectors. So here's the general idea of multiplying matrices if you've never done it before. It's essentially a generalization of the dot product. First thing is you got to make sure that the multiplication is possible. So if you have two things that you're multiplying, so here we're multiplying a matrix times a vector. First thing we're going to do is determine the number of rows and the number of columns for each. So we're doing a matrix times a vector. In this case, we found that the matrix had 2 rows and 2 columns, and then the vector had 2 rows and 1 column when we write it kind of this way in column notation, the way Kittner likes to do it. So again, rows and then columns. So this vector you can think of it as having 2 rows and then 1 column. Now the requirement is that the inner numbers have to match. So if I write that the matrix is 2 by 2 and then the vector is 2 by 1, these numbers have to match in order for the multiplication to work, else you cannot multiply these two things together. Again, you'll see why, because again, it's essentially just a dot product. So these two numbers have to match, and they do, so we're off and running. Then it turns out that the outer numbers give you the dimensions of the answer. So ultimately we're going to take R and multiply it by this matrix, and we're going to, at the end of the day, get something back. That something that we get back is going to have the outer numbers. So it's going to have 2 rows and 1 column, i.e. it's a vector. So the answer is going to also be a vector object. So inner numbers have to match to multiply, then the outer numbers tell you the dimensions of the result. And then you just take, so this result that we ultimately get has 2 rows and 1 column, so there are 2 elements. if I write S, it's something and then something. 2 rows and 1 column. So we have to do 2 calculations in order to figure out what's this number and what's this number. And so this top number here is in the first row in the first column. And so then you just take the dot product of the first row of M with the first column of, this should have been R, first column of R. And then the second element is in the second row, first column. So then you do the dot product of the second row of M with the first column of R. So let's do an example. I want to rotate these axes by 90 degrees. Then I want to determine what is this coordinate in the new coordinate system after I've rotated. So this one, easy to do graphically. If here are the original axes, when I rotate them by 90 degrees, this becomes this. So if this is x, I might call this x prime. And then if this is y, rotating by 90 degrees becomes that. And so then if this distance is 3, it's easy to convince yourself that this distance is 3. But now this distance is not along the x direction, but it's along the y direction. So it looks like now this and the positive direction is that way. So if this is the origin and this is a length 3, looks like then that coordinate is -3 in the y direction. And the x coordinate in this direction, here's 0, it has just a coordinate of 0. Now we should be able to do that mathematically, of course. So first we'll write the matrix. So I'll plug in pi over 2 to my cosines and sines. So the cosines become 0, the sines become 1, then I have that negative sign. And so we could, for example, let's see, what did I do here? I didn't actually, I guess I do it down here. So looks like what I'm doing here is I could take one of the unit vectors and ask, how does the x direction, which is 1, 0, transform into the new coordinate system? How does this vector transform into the new coordinate system? And so what I do is I want to take this matrix and I multiply it by this vector. So I write it here, ignore the colors for right now. So again, I need to make sure it works. 2 rows and 2 columns, and then 2 rows and 1 column. So then I should write it out. Well, I guess it's the same thing up here. 2 rows and 2 columns, and then 2 rows and 1 column. Since the inner numbers match, I can do this. And I know my answer is going to have 2 coordinates at the end of the day. Because again, that is what the outer numbers tell you. It's going to have 2 rows and 1 column. So then I can write it as 2 rows and 1 column, and I just want to figure out what alpha and beta are, which then tell me the coordinate in the new x prime direction and the coordinate in the new y prime direction. Not sure what that is. So let's do alpha first. Alpha is in the first row, first column. There's only 1 column, but so it's the first. And there are 2 rows, and then we start from top to bottom. So first row, first column. So then what I do is I take the first row of this matrix, the first column of this vector. And again, there's only 1 column, so that's easy. First row, first column gives me the first row, first column element. So then I do 0, 1, 1, 0, take the dot product. So then the 0 times 1, then I add to it this 1 times 0, which is that. So again, it's just a dot product. And then that's just a 0. Beta is in the second row, first column. So then I do the dot product of the second row, first column. So then it looks like I have the -1, 0, and then 1, 0. So then it's -1 times 1 plus 0 times 0. Dot product gives me -1. So then what we're saying is, should I make this different color too? What we are saying is that this unit vector, when we transform it, becomes in the new coordinate system just negative y prime. Which, if you stare at this for long enough, makes sense. X hat, right, this is the original vector, and then what does this arrow look like in the new coordinate system? Well, it looks like it is just pointing in the negative y hat direction. So this vector just becomes negative y hat after the I guess really after the transformation. And then similarly, you can convince yourself that y hat becomes x prime hat. So then if I want to do, what does this coordinate look like in my new coordinate system? I could just use these transformations. If I know x goes to negative y prime, then I could replace 3x with 3 times negative y prime, and similarly I could replace that here. And it looks like I get a coordinate of 0, negative 3. I could, of course, just use the matrix again. So I have now 3, 0. I want to know how this vector changes. So again, usual sting. First row, first column gives me this element, which ends up being 0. And then second row, first column gives me this element, which is just negative 3. So then this coordinate transforms into this coordinate, which is kind of what we argued graphically. All right, want something that's a little bit more interesting, then that doesn't have a bunch of zeros. Right, here's, right, if I want to rotate things 60 degrees, then this is my matrix. So then if I want to say, what does this coordinate, which is along the y, if I just look at the black, right, has a component that's maybe 0, 2, how does that transform when I turn it into this coordinate system, which then it seems like it will have a component along both axes? Then I just do, again, the matrix multiplication. This row, this column gives me that, because it looks like it's a half times 0 plus this times that, so it becomes that. Then this 1 is a result of this times this, which then looks like it's that times 0, and then plus that times that. And since all of these things are constant with time, we don't have to worry about any kind of weirdness going on. You can convince yourself of that. That if you can do this with positions, you can also do it with velocities, you can also do it with accelerations, you can also do it with forces. So much that you actually have been doing this with forces, even if you didn't realize this is what you were technically doing. You know, for example, when you're the box on an incline and gravity points straight down, you may have thought, well, I'm going to instead write this vector as a component along the ramp and perpendicular to the ramp. But all you were doing is you were taking your horizontal and vertical axes and rotating them by some angle theta. And so then you can also do that to the vector as well, to get it in components on your new axis or your new coordinate system. Okay. And then, yeah, that's essentially what went on there. Some quick disclaimers, because again, the internet is very sloppy. You might see different things going on. So again, when I wrote down what that matrix was, somewhere here, right, I said that this was that this thing was a matrix that rotated the coordinate axes counterclockwise by theta. So, for example, this set of coordinates rotated by 90 degrees becomes this. This becomes that, and that rotates into that. if you want to think of it that way. So rotating the axes. Though then you have axes that are pointing kind of atypical. Right? Usually you have x kind of going in this direction, and then usually you have y going in that direction, where after the rotation, kind of x is up and y is left, and so it's positive to the left and positive up, which is kind of weird versus kind of what we usually do. So sometimes you'll see it kind of drawn as fixed axes, where you have some axes, x and y, and then you want to do some sort of rotation, but then you still want to write x going to the right and y going up, though some sort of transformation has occurred. So here we kept the point where it was and then just rotated the axes. So then that point then can be identified relative to the new axis directions. Here, if we want it to be equivalent, right, since here we're not moving the axes, but we're stating, if we're using the same matrix, right, that matrix was saying take the coordinate axes and rotate them counterclockwise. But if I don't want to actually redraw them, I can get the same result if I just take the point and rotate it clockwise by 90 degrees. So if you think of it in terms of rotating the axes, then this matrix rotates the axes counterclockwise. If you want to write the axes in the same directions, x right and y up, then this same matrix, you can think of it as what it does is it takes the vectors and rotates them by 90 degrees, clockwise. So these are two equivalent ways of stating things. This rotation matrix here rotates the axes counterclockwise by theta, or it rotates vectors clockwise by theta. Both are equivalent. Now, another thing you'll see online with zero explanation as to which is which, and maybe you were wondering this yourself, right? I wrote down this matrix here. Sometimes you'll see the matrix written down like this, and the negative sign's up here. So what gives? What's going on? Here, of course, we said that this rotates axes counterclockwise, vectors clockwise. And here I can make use of the odd evenness of the trig functions, and note that if I set phi equal to negative theta, then sine of phi is just negative sine theta by the odd property, and then cosine of phi is the same thing as cosine of theta by the even property. So if I make this transformation, then this matrix becomes equal to this matrix. So these matrices are saying the exact same thing, only that one of them is going in the opposite direction. This is doing it clockwise rotation or counterclockwise axes. This matrix is just doing the opposite. So you can, if you want, you can think this one is rotate the axes counterclockwise, rotate the vectors clockwise. This one then rotates the axes clockwise, or rotates the vectors counterclockwise. And you can dream up an example, right? Do an example here. Phi of pi over 2. Here's this matrix. And if I take the coordinate 3, 0, so here's the original axes, here's that point, it has the effect of turning it into 0, 3. So it looks like it takes this point and rotates it counterclockwise to get there. So vectors rotating counterclockwise, which is the opposite of what this one did, because the minus sign's in a different spot. And again, online descriptions, it will just say, like, this is a clockwise rotation. It won't say if it's axes, it won't say if it's the vectors. So, make sure you use some thought before you start just using stuff you find online. Now, in all of these cases, the axes themselves were always anchored. We could rotate from one to the other, but we didn't have to worry about any sort of time derivatives because they were fixed in space and time. These are fixed in space and time, and then we can rotate or tilt our head in order to translate one coordinate system into the other. Now with polar coordinates, we have to be a little bit more careful. So polar coordinates are of course useful when you're dealing with circular motions. We've been seeing that with Kepler's laws. And these have an additional property where they move along with you as you kind of traverse your trajectory. So kind of defining positions in this coordinate system can be a little bit weird at first, because we're going to define the position in this coordinate system based on your distance from the origin. We're going to make that one of the axes. So we're going to make one axis this radial direction. How far away are you from the origin, which you are free to put down wherever the hell you want. Usually with this sort of stuff, since it deals with circular motion, you'll put it at the center of a circle, or the location of the rotation axis, some sane location. So we have this radial direction, which again, we can define our position based on your distance from the origin. That is your position in this coordinate system. So if we call this radial direction r hat, then your general generic distance is just given by r hat. How far are you away from the origin? And then this is the vector that is pointing, towards or away from the origin. And that's it. This r, instead of x and y, now we have this r coordinate, which again, r tells you how far away you are from the origin. How does r change? Well, that's of course just r dot. R dot tells you how your distance from the origin is changing. If it's positive, you're moving away from the origin. If it's negative, you're moving towards the origin. Now, we're talking about 2D space here. So it might be confusing at first that there's not a second unit vector here to specify your position. But again, that's based on the definition here, that our definition is based on your distance from the origin. So this alone specifies your position in this coordinate system. And so you might be saying, well, if this is my origin here, and I have this vector here that gets me out to that point, and then what about if I have the same vector but kind of rotated here? What I'm saying is that those two would be written down exactly the same in polar coordinates. And that's exactly right. Because again, your position is just based on distance from the origin. This orientation you're drawing, where this one's horizontal and this one is at an angle, I could say it's horizontal relative to what? Well, you're probably using this, the grid lines on the paper. So in a sense, you are laying down a Cartesian axis so that you can specify horizontal versus vertical. There's no reason why you had to write, you had to say this was horizontal. You could have said this was horizontal, and then this would be, this was horizontal, then this would be vertical, for example. So if we call this our position from the origin, the other direction, which we'll call the tangential direction, is telling you how this vector moves. So if I have some origin here, and here's my position from the origin, this tangential direction, pointing up, again, so it obeys the right-hand rule, r cross theta will point out the page, like a good 3D coordinate system, cyclic coordinate system. This vector here points to your coordinate, and then whatever is going on in this direction is going to tell you how your position vector moves. Because remember from intro physics that, this, just think velocities and positions. This is position, and you have a velocity that is perpendicular, that will only change the direction, not the magnitude. And similarly, if you have a position vector, and then you have a velocity that is parallel or anti-parallel, that will only change the magnitude, not the direction. So if our position is based on position from the origin, then this second dimension, which we do need because this is a 2D coordinate system, can't have a position associated with it, because that only tells you how your position vector will change, not give you a position itself. So it makes sense that this coordinate will pop up in velocities and accelerations, but it has no role in position, because your first coordinate says everything you need. So we have the radial coordinate direction, and then we have this tangential direction, which is perpendicular to it. And then, like it's usually taught, if we do want to lay down some Cartesian axes, then I can specify a unique value of theta. If I have some point here, I can specify it has some, I can specify its position, distance from the origin, and I can orient it by this angle theta. Really what I'm doing is I'm orienting it relative to the Cartesian axes. They have nothing to do with the polar coordinate system. But that's what we usually do, so we can more easily visualize this kind of 2D space. So I think that's all well and good. And the nice thing here is if the kind of rotation matrices and all that made sense, if you think of these coordinate systems, here's your Cartesian coordinate system, and then your position from the origin, and then that direction is r hat, and the direction perpendicular is theta hat. Comparing this to this, and then this compared to this, well, that looks like it's just a rotation, going here and then rotating it to here. Or if I'm all the way out here, I sweep out this whole angle here. So then if you just imagine r hat swinging around, and r hat points that way, then theta hat swinging around, theta hat then points that way. So, and again, that looks like it's just a rotation of this into that. The only thing we have to be careful about is that since these axes move with the particle, that means time derivatives don't necessarily vanish. And again, you do not need to necessarily have circular. I could use polar coordinates for any motion, right? I could be traveling a straight line. I could write in polar coordinates. Would not necessarily make my life easier. Would probably make it harder, actually. But we do have to be careful in making sure we know kind of how this theta is changing with time, because that then changes the orientation of our coordinate system, which then affects how we define position, velocities, and accelerations. So the easy part is that since going from this to this is literally just a rotation, we can write down what r hat and theta hat are in terms of x and y. And they are identical to what we had before. And then, if you want to actually calculate the coordinates, given x and y, this is how you get r and theta, or given r and theta, this is how you get x and y. Those should all look pretty familiar, just Pythagorean theorem. What I want to remind us about now is let's do time derivatives. I can define my position, where is it, as this. The velocity is then the derivative of this thing, but that means I have to take the derivative of r, which will just become r dot, and I have to ask myself, what is the derivative of this unit vector? Well, this was all well and good. And when we took the derivatives before, we didn't have to worry about theta derivatives, because those axes were fixed. The Cartesian axes were fixed. Here, since the axes move with, when you take the derivative of this unit vector, the cosine becomes negative sine, but then it's a time derivative, so it pops out by the chain rule, theta dot. And then, of course, the derivative of x is 0. So once you do the product rule of this, it just becomes that. And then similarly, sine becomes cosine, chain rule pops out that, y hat goes along for the ride. And then if you stare at this, and then you stare at this, notice that the derivative of r hat is just theta dot theta hat. And similarly, convince yourself, derivative of theta hat just becomes negative theta dot r hat. And then we're off and running. Here's my general position. By definition, the velocity is the time derivative of that vector, which again means that I take the derivative of this times that. That's that right there. Then I add to it this times the derivative of that. So then that is that right there, where again I've replaced, I know that the time derivative of the unit vector is theta dot theta hat, so then I have two terms. And again, there is a term that's along the radial direction and a term that's along the tangential direction. Here it appeared. And again, that makes sense because we figured that this direction had something to do with how things changed in the radial direction. So then my velocity components are r dot in the radial direction and then r theta dot in the theta direction. Note that just by units, if you were to say it's r dot theta dot, I would immediately take off points because I would say the units don't match. If this is a velocity, then this is a position over time. And if I had just had theta dot, well, that's just dimensionless divided by time. So it'd be hertz or something. So I know that there has to be some thing that has a dimension of length. So here's how the units end up working out. And again, we can ask the question, how does r change? How does my distance from the origin change? That, by definition, is r dot. So in this case, how does r change? I look at the radial component of velocity, and that tells me r dot. Now, what about the rate that I'm kind of spinning? How my axes are going from here to here quickly or slowly? What's going on? So I might ask, how is theta changing? Which then governs the kind of orientation of my axes. Well, it's not just that I look at this component and get theta dot. I look at this component and get r theta dot, which then I could solve for theta dot. But unlike Cartesian, where I just looked at the x component and I got x dot, looked at the y component, I got y dot. Here I look at the radial component and I get r dot, great. Then I look at the theta component and I get r theta dot. So then r theta dot is called the azimuthal velocity, where this is the radial velocity. That's the azimuthal. The rate you're moving in the radial direction, and this is the rate you're moving in the azimuthal direction, which then has in it information about the rate of kind of rotation. Then do it again to get accelerations. And you get something that in the radial direction, you have r double dot, and then you have this other term, the centripetal term, r double dot minus r theta dot squared, all in the r direction. And then you got r theta double dot plus 2 r dot theta dot. It's called the Coriolis term. And this is the angular acceleration. So again, I could define the radial acceleration, a sub r, but a sub r in this case is this entire thing, which has something that's telling you how r is changing, or really how r dot is changing, and then it has this term here, the centripetal term, which doesn't seem to say anything about how r is changing. So, and I think I was a little unclear in class about this. Right, if I want to know how is r dot changing, that is by definition r double dot. But I can't just look at this component and get r double dot immediately. Whatever is in this component is r double dot minus r theta dot squared. Then the tangential or azimuthal acceleration has, again, two terms, an angular acceleration component and a Coriolis component. And then, of course, the units all work out well and good. So, these are just formulas. Usually, there are some restrictions we can do that make our lives a lot easier. So here they are in general. Good place to start. General position, general velocity, general acceleration. So again, if I said v in polar coordinates was kind of 3, 2, then that would be saying that 3 is the same thing as r double dot, as r dot, and then 2 is the same thing as r theta dot. So then if I knew r, I could then get theta dot. But it's not just 2. Anyway, here's the general results. If I then know I'm also constrained to move on a circle, Like suppose I know I'm on a circular track, or I'm on a roller coaster or something. Then I know then r is constant. The distance from the origin will be a constant, which then means the derivatives will vanish. And then my life simplifies a little bit. Position just becomes the constant r comma 0. The velocity simplifies because this term is gone, and that just becomes capital R theta dot. So then the velocity only has one component, the azimuthal velocity, which is this r theta dot. Not necessarily a constant, because the thing could be speeding up or slowing down. So again, if you're constrained to move on a circle, then your velocity is this theta, v theta, which is always tangent to the circle, compared to the radial velocity, which is kind of pointing in or out, towards the center of the circle. And then your acceleration, again, r double dot goes away, r dot goes away, becomes the centripetal term and this angular acceleration term, which if I use this, I can write the centripetal term. That might look familiar, negative v squared over r. That is the kind of center-seeking acceleration, that it's not making you move closer or farther away, but it's kind of helping you stay in a circle by changing your direction. And then this is the angular acceleration term. In introphysics, we usually use alpha, so we might have written this as r alpha, where this would written as kind of r omega, I think usually the introphysics books use. Really, this is saying something about r dot and r double dot. If, in addition, you also know it's uniform circular motion, which then this azimuthal velocity is a constant, well, I already knew that r is a constant, so then that means theta dot is a constant in uniform circular motion. So then I could call theta dot omega. And then these simplify even more, because then I can write position doesn't change, velocity then becomes r omega, which now it is also a constant vector. And then the acceleration, now this term goes away, because this is a constant, so its derivative will be 0. So then this is the acceleration, which again I can write like that. So the thing with Newton's laws, this I think is going to end up being our computational problem that we play around with later this week, is that if you're going to do a Newton's law problem, this is the acceleration you plug in if you're using polar coordinates. You figure out the forces in polar coordinates, and then you set it equal to m times this acceleration. Where before, that acceleration was pretty simple. Gosh, it's longer than I realized. Where is the acceleration? There we go. In Cartesian, it was pretty simple. X double dot, y double dot. In polar coordinates, the acceleration is a little bit more involved. It's usually why these things have to be done on a computer. So for example, let's just go very briefly, because we'll see this problem again. If I'm on this cart, I'm going over this loop, I might want to understand my velocities and accelerations and know how fast I need to be going, so that I don't go. So once I get to the loop, it makes sense to use polar coordinates. I'm moving in a circle. Why not use polar coordinates? So I'll put my origin in the center. I'll define theta based on kind of my starting spot, when I first get into the circle. So I'll have theta be defined in that direction. So then when the cart is up here, we have the radial direction and the theta direction. When the cart is here, we have the radial direction and the theta direction. When the cart is here, we have the radial direction and the theta direction, which are moving along with you. We're constrained to move in a circle, so I know that I can set r equal to this fixed constant. R dot and r double dot vanish. And I can then write down that the acceleration must therefore, I know it's not going to be uniform circular motion, because gravity is going to sometimes be really working against me, sometimes working with me. So I'm going to use this acceleration. I took this, I was constrained to move on a circle, that simplified the acceleration of that. This is what I plug into Newton's laws. Once I figure out what all the forces are. So, again, if the box is here, is it touching anything? It's touching the coaster, so I know there's a contact force, the normal force you might call it. And notice here I wrote it as in polar coordinates, -n, because it's pointing radially towards the center, and there's no azimuthal component for the force, because it points, this is r hat, the contact force points in that direction. And then gravity, which points straight down, I can decompose it into the radial component and the theta component. And since the positive directions are this way, it looks like the gravity has a positive radial component and a negative theta component. So then that's where these come from. And also looking for triangles. If that's down and that's radial, and that's also theta. So then we have some positive, when it's here, when theta is say 30 degrees, this will be positive away from the origin. This will be negative, which means kind of in opposing or in the negative theta direction. So then my net force then is the sum of the two. So I have the radial components and then the theta components. And then what I do is I set that equal to m times the acceleration, but then I use the polar coordinate acceleration instead. That then gives me two differential equations, which are a little bit more involved. So if I set this equal to that, that's this differential equation, which is saying that the second derivative of theta is equal to that, which note when theta is less than, it should be less than pi, when it's anywhere here, notice that this entire thing is a negative number, which makes sense because that means the rate that you're rotating is slowing down. So you're slowing down in rotation up to here. Then once you get to here and go on, you'll notice that theta double dot is positive. So then theta dot gets faster, larger and larger, and that means you're just rotating faster and faster. But then this cannot be solved by hand. Because again, it's theta these are time derivatives, and this is theta as a function of time. Solve it numerically. And then in the radial direction, I have that equal to that, which is again a differential equation, but it has this contact force n, which can be whatever it wants in order to ensure that you're not going through the floor. But if we did all the work to numerically solve this thing to get theta as a function of time and theta dot as a function of time, which we'll review, then you can just plug those numerical answers into this and this, and then you can evaluate the value of n, using your numerical solutions. And then you could calculate, for example, how fast you have to be going initially so that you do not fall off the track, which will help us review some numerical integration. There'll be some root finding, there'll be some interpolation, lots of good stuff. But, okay. Hopefully that was clarifying if some of that stuff was new or it's been a while.